what are the signed numbers? In the earlier session we studied about it. So basically the numbers are represented in unsigned and signed manner. So unsigned numbers are the numbers which are always positive numbers, and signed numbers are the numbers which can be either negative numbers or positive numbers. So we have already studied about it. Now let us look into this binary multiplication. So here we are going to multiply two numbers, that is 5 and 3. The binary equivalent of 5 is 0, 1, 0, 1, which is also called as the multiplier. 3 is the multiplicand. We have converted its binary equivalent to its binary equivalent, which is 0, 0, 1, 1. The product is 15. So the answer, that means the answer of 5 into 3 is 50. Now what we have done over here is, we have multiplied this multiplier with the multiplicand. Okay, this is how we multiply this first bit. This first bit will be multiplied by all these bits. Again we go to this bit, then again multiply. So likewise. Now the answer that comes is 0, 0, 0, 1, 1, 1, 1. This is nothing but equivalent of 50. So this is positive 50. Now let us consider the other scenario. Other scenario is what? Let us consider I want to multiply 5 into minus 3. So here if you observe in this particular part, both the numbers are positive. But here one number is positive and one number is negative. So if I perform multiplication of 5 into minus 3, the answer should be minus 50. Now if you remember, negative numbers are always represented in its 2's complement form. So if I want to consider this minus 3 into representation into the computer's memory, what I have to do is, I have to first convert that into its 2's complement form. So what is the 2's complement form of minus 3? It is 1, 1, 0, 1. So what I will do, I will multiply 5 with minus 3 ka 2's complement form, which is 1, 1, 0, 1. So now see, here if you see, it is 0, 1, 0, 1, which is equivalent of 5, and 1, 1, 0, 1 is nothing but the 2's complement of minus 3. So now I will multiply and I will get the answer as 1, 0, 0, 0, 0, 0, 1. Now what would be the answer that we would be getting? Ideally it should be minus 50. Now if I do minus 15 means the number is negative, that means whenever I want to know the number, or whenever I want to get its binary equivalent, what I have to do? I have to take its 2's complement form. So let us see how to take the 2's complement form of 50 minus 50. So 0, 0, 0, 1, 1, 1, 1 is nothing but the binary equivalent of 50 plus 50. Now first we have to do is find out the 1's complement of 50. So how do we find out 1's complement? Invert the bits, that is we will replace 1 with 0 and 0 with 1. So here see, this number is represented over here, and 0 will be replaced by 1, 1 will be replaced by 0. So likewise this number that we got is nothing but the 1's complement of 50. Now to get the 2's complement, we will add 1 to it. 1 to what? 1 to 1's complement. So what is the 1's complement? 1, 1, 1, 0, 0, 0, 0. That we have written here, and we will add 1 to it to get the 2's complement. So it is what? 1, 0 plus 1, 1, the 0, 0, 0, 1 as it is, 1 as it is, and 1 as it is. So the 2's complement equivalent of minus 15 is 1, 1, 1, 0, 0, 0, 1. So this is how we represent minus 15 in 2's complement form. So ideally we should get this value when we multiply. So are we getting that value over here? See, 15's ka 2's complement is 111, 000, 1. Are we getting this value over here? No. So there is something wrong. So see, we will check this. We have multiplied, the answer is 15. After the answer is 15. Now here what? 5 into minus 3, that is minus 15. Minus 15, its uska 2's complement form is what? 1, 1, 1, 0, 0, 0, 1. Right? And after multiplying this, what we are getting? It is 1, 0, 0, 0, 0, 0, 1, which is not equal. So when it is not equal, that means there is some discrepancy. That means there is wrong representation of the data. So what we can conclude with this is that binary multiplication method works only with unsigned numbers. That is, it works only for positive numbers. But when negative numbers are included for multiplication, it gives wrong answers. That means it fails for signed numbers. Therefore, there was some method to be evolved or introduced for signed numbers multiplication. So what was that method? That method was called as Booth's algorithm. So see, therefore Booth's algorithm was introduced for signed numbers multiplication. So 8 into 5, both the numbers are positive. Here, binary multiplication can work very well. But what if we want to multiply this signed numbers? Signed numbers are what? 5 into minus 3. One is positive, one is negative. It becomes a difficult task, or it gives incorrect answer if we do it by binary multiplication. So Booth's algorithm was introduced. Now before going to actual algorithm, I want you to know the basic addition rules. So what are the addition rules? So 0 plus 0 becomes 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 0 with carry 1. Now I want you all to perform the binary addition of these two numbers, which is 1101 and 1001. Okay, so do it, students. So see here, I have represented A as number 1, which is 1101. Then second number is B, which is 1001. Now I perform the addition. 1 plus 1 is 0 with carry 1. So I have written here C is equal to 1. So this 1 will come as it is here. This 1 plus 0 is 1. 1 plus 1 is 0 and with carry 1. So this carry is 1. So the answer is 10110. This is how we perform binary addition. Now I also want you to know this arithmetic shift right operation, because we will be learning this in the algorithm. So see here, Q0, Q1, Q2, Q3. If you are seeing this, this is nothing but the bits in that particular number. So if I am representing 1101, which means that the number is represented in 4 bits, starting from Q0 to Q3. Now if I want to perform arithmetic shift operation on this number, how will we do that? So we will shift the bits to the right by 1 position. So see here, let us come from the right hand side. So which is the bit number which is Q0? What is the value of Q0? It is 1. So we will shift 1 position to the right. So this 1 will move out. It will not be stored anywhere as of now. Then let us move to the next bit, which is Q1. Q1 will shift 1 position to the right. We have only 4 bits, so it will move to the extreme right. Then we have Q2, which is 1. It will be shifted 1 position to the right. Third will be shifted to Q2 bit. Now this bits remains empty. Now what to be filled? This Q3 bit will be filled with the same number as Q3 bit in the earlier representation. Am I clear? I'll tell you one more time. We will start with the rightmost bit, that is Q0. Then we will come with to Q1, then Q2 and then Q3. Q0 will be moved out because it will have no place to store, so it will be moved out. The rest bits will shift 1 position to the right. So this Q1 will shift here, Q2 will shift here, Q3 will shift here. But what do we write in this? Because we do not have Q4 bit, so this cannot be shifted like this. So what do we write over here? So what do we write? We write or we repeat the same bit that is there in Q3 in this particular part. Am I clear? Okay. So let us see the flowchart of Booth's algorithm. We will start. Then we will have 4 parameters. A stands for accumulator, which will be initialized to 0. A is the accumulator wherein all the results will be stored in a temporary manner. Q minus 1 will be initialized to 0. That is the bit. I will tell you what is that. Then M stands for multiplicand. Q is the multiplier. Count is N. N is nothing but how many number of bits are there. And if there are 4 bits, that means this algorithm will work for 4 passes. That is nothing but this N. That means N, if the count is N, the algorithm will work for N passes. Okay, now after initialization, what we will do, we will compare the bits Q0 with Q minus 1. We will compare its values. If it is 0, 1, we will add M, that is multiplicand, with the accumulator value and store it in the accumulator. If Q0, Q1 has the combination of 1, 0, what we will do is we will subtract this multiplicand from accumulator and store the value in accumulator. This is the first step. Now, let's say if Q0 and Q1 have values 1, 1, 0, 0 after comparison, then we will only perform arithmetic shift right. Of what bits we will perform? We will perform arithmetic shift right of accumulator Q and Q minus 1. Then count will be decreased by 1. So here, if you see, if I have 0, 1 value and if I have 1, 0 value, for 0, 1 I will perform first A is equal to A plus M, then I will perform arithmetic shift right. If value is 1, 0, then I will first perform A is equal to A minus 1 and then I will perform arithmetic shift right. So in both the methods, the second step is to perform arithmetic shift right. And only when the comparison values are 1, 1 and 0, 0, you have to perform only one step, that is arithmetic shift right. Now till how much time we have to do this? Till the time count becomes 0. Till that time we have to perform these steps, and once the count is 0, we will end this algorithm. Now you will be able to understand this concept with the example more clearly. Now let us take one example, that is you want to perform silent multiplication of let's say we will take two positive numbers, that is 7 and 3, which is simple. The next example I want you to solve is 7 into minus 3 wala. Okay, I will give you example for solve. I am taking an example to solve both the numbers positive. So see, what is the multiplicand, which is 7. That is first we have to take its binary equivalent. So here 0, 1, 1, 1. Now you again will have a doubt in your mind why we have not taken 3 bits, because 7 can also be represented by 3 bits, that is 3 ones can be is equivalent to 1. But see, if you remember in signed and unsigned numbers, I had told you if I use 3 bits, can I represent this signed numbers? Can I represent 7 into the range of minus 4 to plus 3? No. That is why I have to represent 7 using 4 bits. So the binary equivalent of 7 in 4 bits is 0, 1, 1, 1. Similarly is the case with 3. Now again you will have a doubt here. The 3 can be represented using 3 bits. Yes, it can be represented, but for simplicity purpose, if the multiplicand is of 4 bits, we have to write this multiplier of 4 bits only, right? So both the calculations becomes a easier task. So both we have to write in same digits. If this is having 4 digits, multiplier will also have 4 digits. Now in the algorithm, if you might have seen, we require plus m ka value as well as minus m ka value. So plus m to see here, we require minus m value, we require plus m value. So for simplicity purpose, what we will do is at the initial process only, we will find out what is the value of minus m. So if plus m is 7, minus m is obviously going to be minus 7. So whenever the number is negative, we will store it into its 2's complement form. So this is the 2's complement representation of 7, right?